Recording. Good afternoon, dear students. So, resolved all my connection issues. Our topic for today is linear spaces. This topic is a little bit complicated for your understanding because, by the way, whole linear algebra is a little bit complicated because it's abstract and it can be scary for the first reading, but nevertheless, we will solve some exercises and it will be easier. By the way, what do you remember about linear spaces? Just please give me a definition. So, who wants? Raise your hands. So you don't remember, right? Okay, let me explain you again. So you don't remember it from lectures. So this is the symbol of a linear space. Oh, no, not so bold. So like this capital L, interesting style, and this is the space of any elements. So maybe vectors, maybe matrices, maybe just numbers, and it has addition, sum operation, and we know that this operation has the next properties such as commutative property, associative property, so we can just take brackets away, and also multiplying by the scalar element, so means to multiply just by number. So that you actually know already, and this product also belongs this linear space, and there are some also as well. So any questions about it? Or no questions?
No questions.
Mm. And also we have the kind of zero element. So it means that if we add a zero element to it, nothing changes. And yeah, also a negative element. So that means so that has the next property. So if we add this negative element, the result will be the zero element. So such rules are obvious, I believe. Okay. Mhm. So let's go to our exercises, and the first exercise is to define if a system of vectors is linearly independent in the linear space of square matrices of given order. So the second order and the third order. Yeah, it can be a little bit confusing, that system of vectors, but vector also doesn't mean only a vector like a set of so like it like a row or a, a column of matrix. It's like abstract. So general meaning of the vector is like an element. So in terms of linear algebras, matrices also can be called vectors. Uh, any ideas how to solve this example? What does linear independency mean? By the way, do you remember it? So raise your hands if you remember. I guess that nobody. Okay. Uh, general. Oh, Sophia. Yeah. Go on.
I may be wrong, but the system is linearly independent when it has a unique zero solution.
It it's a kind of yeah. It can be a kind of definition for this case. Yeah, actually, it will be the solution of our first exercise. But what does so if we have some vectors like A, B, and C, and this system of vectors is not linear dependent. Yes, so yeah, so the general definition is that such a sum that so would okay, I will write and then explain. So alpha 2b and alpha 3c, and it equals 0 only if alpha 1, alpha 2, and alpha 3 are zeros as well. So yeah, so only so if this alpha 1, 2, and 3 are non-zeros, so if any of them is not 0 and this sum is 0, it means that these vectors are linearly dependent. How to explain it simpler? It means that, for example, we can express C as a combination of uh, this okay yeah, combination, a linear combination of other elements. So we can find some coefficients with which we can express the third one. Do you understand what I mean, or maybe any questions for now?
No questions.
No questions. Okay, let's go to the task. Now we will solve only a part. So what do we have? What we have to do? We do the next thing. We need to, so we need to check if it's linearly independent. So we need to find such alpha elements for which such condition is true. and the result must be zero matrix. So it will look like this. And now let's calculate. So alpha 1 and alpha 2. So we just need to add these matrices. So alpha 1 here is 0, so moving next. Here is 0, but here we have 2 alpha 2. So added the first row, and let's add the second row. Minus alpha A plus alpha 2. So just remembering matrices, adding alpha 2 and alpha 1. And it must be equal zero matrix. What can we see? Are here any non-zero solutions for such a system? So can we find non-zero alphas here? The answer is obvious. So who can answer? So Bogdan?
Yeah, the answer is alpha can only be 0.
Yeah, so only 0, and it, as was mentioned before, yeah, so the system has only trivial solution, and it means that the system of these matrices is linear independent, because we have non-zero alpha, and in the answer you must always write so that therefore the system is linear independent. What we had to prove. So what was required to prove? Don't forget about it. Okay. Maybe any questions about this task? Or no questions?
So the system is linearly dependent, right?
No. It's linearly independent.
Independent. Oh,
Because we have no non-zero alpha for which this equation would be right. So not
okay.
such non-zero alphas, only 0. Maybe some more questions? Okay, let's move next. And then I have the next question about B. We won't solve it now, but I have a question. How many alpha elements do we have to find in B? Sophia, maybe anybody else? Some new people who wants to join our discussion? Maybe Vadim? Oh, Dmitro, yeah, go on.
So by alpha, you mean alpha 1 and alpha 2?
But how many alpha? Yeah. How many?
So 2 alphas, and the third one will be the C vector,
Hmm.
or is it 3 alphas?
So we have uh, 3 matrices.
Yes.
And we need to prove that all of them are linearly independent. So how many alphas?
3.
Yeah, 3. So we need to prove that alpha 1 plus alpha 2 multiplied by this matrix plus alpha 3 multiplied by these vectors equals 0 matrix. So theta Greek. So that this equation must be equal to, so this sum must be equal to zero matrix. So, and only if all of them are zero, alpha 1, alpha 2, alpha 3, so it means that the system is linearly independent. So no questions, yeah, how to solve. It will be a kind of your home task to practice more. Okay, let's move next. We have the next task. So now we'll solve only part 2, and we'll have to find a basis of a system of linear algebraic equations. Let me move it here, and I will erase part B because now we will solve part A, and maybe anybody knows how to solve it. So find a basis and define a dimension of the linear space of this system. So linear space of system solutions. So we see that it's a homogeneous system of equations. You had already practiced with it. You know how to solve them. Any ideas, Matvey?
Well, we write down our elements for determinant or for matrix and solve by method by Gaussian, I think.
Yeah, it will be convenient to use Gaussian method, of course.
So let's solve it.
Yeah, but so actually, yeah, yes, this is correct. So you mentioned correct steps. We need to solve this system of linear equations, and the basis actually will be so a set of non-linear, so linear independent solution. So we need to find a general solution and then some partial of them. Actually, the idea to find a fundamental system. Okay, let's go. Let's start solving. Now I will do it in my own, but it would be nice if so just follow, and if something goes wrong, just feel free to raise your hand and ask the question. Maybe if something not understandable during the solution. So now we will just use the Gaussian elimination method. So let's copy and paste. Here we just set zeros. And we need to subtract the first row from the second. So here we have -2, 2, and -2. And from this row we must multiply, or we must add, we must subtract the first row multiplied by 3. -2, 2, -2. And yeah, continuing. -4, 4, and -4. So some of them are going away. So these elements, so remember, these rows, because they are identical, and we can, by the way, divide by -2 just to save plus here. Okay. So x1 plus x2 minus 1, 1. By the way, what is the rank of the matrix?
2.
Rank is 2, but yeah, correct. And no one told me that I was doing something, some bad things. No one told me. So, basis variables are x2, x1 and x2, and free variables are x3 and x4. Mhm. And let's mark our free variables as constants. So just for easier understanding, for easier calculations. And now we will, yeah, let's solve the system with respect to our solution. Yeah, let's find first our general solution, and then we will move next. So x2 equals c1 minus c2, and x1 equals, so x2 minus x2, by the way, plus c1 minus and minus c2. Yeah, so yeah, that's correct. And by the way, so what we have, so just minus this. Yes, and it just equals 0. And here it is. And let's write down the general solution. That's just a partial case. So here is C1, C2, 0, C1 minus C2. and the basis will be the fundamental system of solutions. By the way, let's write it in such a way, so correct form of recording. So depending, so firstly we set 1 to the first free variable. So 0, 1, 1 and 0. And the next solution -1, 0, 1. So what was our, yeah, so here is the basis for here is the basis for the space of general solutions of the system, these vectors. And who can answer what is the dimension of this space? So can anybody answer? Any ideas? Bogdan?
Maybe 2,
Correct, 2, and why?
because of the rank of matrix is 2, if I'm not mistaken.
Yeah, it's correct, but and also because of because number of bases of elements that that form the basis is equal to 2. But yeah, in case of linear algebra equation system, these definitions are equivalent. Yeah, that's correct. Any questions about these tasks? This task? No. If you have questions, don't be afraid to raise your hand. Pavo, you wanted to tell something?
I want to tell no questions.
Okay, no questions. So no hands, no questions. Let's move next. Okay, the next exercise, exercise 3. Let's copy and paste it. And I will clear all my drawings. Not all, will leave some theoretical material. So we have so given vector x, and we need to find its coordinates in basis beta prime. So this one so we need to find coordinates in basis based on such vectors e1 prime, e2 prime, e3 prime. Who remembers how to solve? Yeah, we know some so a couple of lessons ago with vectors we did so we solved the system of equations, but now we will do other thing with that. So we will solve it in another way. So who remembers? Who can answer? Raise your hands. Okay, nobody remembers. Well, now let's write. I will write the next formula. So, so x prime, it will be the coordinates of a vector in the new basis. And how to get it? I will write the formula and then we'll explain. So, do you remember what is matrix T? Sophia?
The matrix of the transition.
Yeah, this is the matrix of the transition from one basis to another. So we need to firstly, so how to solve? We need to build a transition matrix, inverse it, and then multiply from the left side by x. So but, x must be multiplied by from the left by this matrix. And how to do it? So do you remember maybe how to build such matrix in this task? How will it look like? Bogdan?
I'm not sure, but I think we need to take the coordinates of these three vectors E,
Mm-hmm.
maybe,
Mm-hmm.
and this is going to be transition matrix.
But
And
how
then with, yeah,
how are we going to build? So we take coordinates, and how are we going to write? So rows or columns?
I think columns.
Yeah, we will use column views. So now let's rewrite all our vectors. So vector x that must be that we must transfer. Then so e1. One, 1, 0. E2. Uh, 0, 1, 1. E3. 1, 0, 1. So let's double check it. -1, 2, 1. Yeah. 1, 1, 0. Correct. E2 correct as well, and E3 as well. Okay, and now let's build our transition matrix. Now we need to calculate its determinant. So 1 plus 1 minus 0 0 and 0. So it just equals 2. Yeah, correct. And now let's find cofactors. Such interesting task. Okay. One. By the way, let's write such way. Yeah, let's write down all cofactors, and then we will write the matrix. So 1, T, 1, 2, minus 1, T, 1, 3, 1, zero, minus 1, yeah, and 1 because of odd power. One. And you follow attentively if everything is correct. Minus 1. One. And the last one. Okay, so our
Can I have a question?
yeah, of course, answer question.
We have
or ask.
a minor T1, 2.
So T1, 2, yeah. So
Yeah. It 1 and 2. It will be the matrix 0 or 1, 0, 0, 1. Is it
One.
minus 1?
1,
Yeah.
0. So 1, 0, 0, 1.
Yeah,
Yeah.
it will be 1 multiplied by 1 minus 0 multiplied by 0. It will be 1, not minus 1.
But
I'm
it's
just
not a minor, it's a cofactor, algebraic
cofactor.
complement. So do you remember how to calculate it? So it is written, so we write it in such way. So minus 1 in power of
Yeah,
I plus j
sorry. I recall, yeah.
multiplied by the minor. So don't forget such important things. So maybe some more questions. Okay, no questions.
No questions.
No questions. So let's move next. So the inverse matrix, the determinant 2. So 1 second. And this matrix must be transposed. So I will. So this row will be the first column. Ran out of space. Okay, let's make it larger. That's not a problem for us. So and now let's find our new coordinates of our vector. And what we basically do, we just multiply it from the left side on our matrix. And this vector also can be copied and pasted. So we'll leave 1 second out of the brackets now. So -1 plus 2 minus 1. By the way, so here we like usage of scalar production. So we multiply this vector by this vector in scalar case. So maybe it can help you better understanding matrices multiplication by the vector. -1 minus 2 plus 1. So here is 0, 4, and -2. And finally, multiplied by 1 second, so 0, 2, -1. And here is so here we have coordinates of vector x prime in the new basis. And also, how can we write it? So x prime equals, so 0 e1 prime plus 2 not a good plus, plus 2 0 2 prime minus 0 minus 1 e3 prime. Okay, any questions about this task? Or no questions?
No questions.
No questions? Okay, let's go for a break now. And then we will continue in 5 minutes. Okay, let's continue. I will erase everything. Almost everything. Okay, and we will move to the next part of our lesson. What do you remember about Euclid space? What is it? Which properties it has? So who remembers?
It's a space with two coordinates like x and y.
Hmm. In our task, yes, but generally speaking. So maybe maybe you remember something from lectures. Okay. Oh, Bogdan. Yeah, go on.
If I'm not mistaken, our space is Euclidean if our these two vectors 6 and I can be matched with real numbers. Not sure.
I guess I understand what you mean, but let's tell it more correct. So Euclidean space is the space is a partial. By the way, it's a partial case of linear space for which we have such operation as scalar product, which we already know. So it is defined in this space. Yeah, and this scalar product uh, is the number. So it was actually correct. And how to the magnitude of the element or its norm is can be found with using the square root of Euclidean. So the square root of scalar production of the element by itself. Actually, what you already did. So, what we were doing yesterday, if I'm not mistaken. It's like general. When length or magnitude of element, it's like a general definition. So nothing specific in this task. But just not to get lost. So we need to find the magnitudes, their scalar product, and cosine of angle. So just kind of revision of our previous lesson. So let's do it quickly. So firstly, we multiply x by y. And it is 1 by 2 minus 3 by 3. So 2 minus 9 minus 7. And let's find magnitudes. So with using a new definition. So we'll multiply x by itself, which is the same that is the same that we do what we do yesterday. So 1 square 1 plus Okay, let's write 9 and so square root of 10. This is the magnitude of x, and then magnitude of y. So square root of scalar multiplication of y by itself. Four plus 9 square root of 13. And the cosine of the angle phi between these vectors equals the scalar product divided by magnitudes, divided by product of magnitudes. So -7 by the square root of 130. And just to verify, so minus square root of 49 divided by square root of 130, so it is less than 1, so just we have adequate answer. Okay. So any questions about this task?
No.
No questions. Okay. Let's move on next. So task number 6. Mhm. Okay, so we have just so we have a basis in Euclidean space, so just 3 not coplanar vectors. And what we have to do, we have to build orthonormal basis. And what does orthonormal basis mean? Who can answer this question? So how to solve actually? No ideas, right? So what is orthonormal basis? Okay, so orthonormal basis is such a basis for based on elements, so ey for which the magnitudes are equal to 1 and e1 so like so ij, so their basis their oh no, that's not correct. So scalar product over such vectors e with index I and e with index j equals 0 if I doesn't equal j. So just let's remember our unit vectors in 3D space. So that correspond coordinate axis x, y, z. So we know that. So I, j, and k. So if we multiply them, so if we multiply them between each other, we will get 0. So that means that they are orthonormal, and so if vectors are orthogonal, their scalar product is 0, and they are like so. This is the basis of orthogonal and unit vectors. So both orthogonal, both unit. Who knows how to solve? How to, firstly, we need to build orthogonal basis. Okay, so you don't remember. We need to, firstly, we need to find orthogonal vectors f1, f2, and f3. How to do it? So f1, so we will do it recursively. F1 is will be G1. Yeah, by the way, vectors. Okay, I will maybe use another character for F because maybe not understandable. And F2 can be found like that. So recursively, G2 plus alpha 1. So it's an index, upper index, not power of 2, and multiplied by f1. So our task is to find a alpha coefficient, and for f3, we need to do the next. So G3 plus alpha 1 with upper index 3 multiplied by f1 plus alpha 2 with such index multiplied by f2. Okay, we will start solving, and then it will be more understandable. So it's such some kind of recursion, maybe, you know, a dynamic programming method. So actually, it's kind of a dynamic programming usage. So firstly, we need to find alpha 1, and how to find it, basically. To find this coefficient, alpha 1, 1, 2. So obviously, it is it can be found from so we know f1 yeah, so it is the so can be found in such way. So we know f1 and g2, it will be a fraction, so we need to divide f scalar product of f1 and g2 by scalar product of f1 by itself. And let's find it. So f1 by g2, so 1 by 0 plus 2 by 3 minus 3 by 2. And so 1 by 1 plus 2 by 2 plus 3 by 3. And it equals, so 6 minus 6, so 0 minus 0 divided by 14. So yeah, everything is correct. So it just equals 0. So our task becomes easier. So f2 equals g2. It equals 0, 3 minus 2. And now we have to find f2. How to do it? We need to find coefficients alpha 1, 3, alpha 2, 3. So by the way, what does this indices mean? I will just remind you. So a lower index is just order of alpha element. So how many alpha coefficients we have, its number, and upper index is iteration. So we are moving to the third iteration. Okay, how to find it? So alpha 1, 3. So the next expression, f1 multiplied by g3 and divided by scalar product of f1 by itself. So f1 by g3. So 1, 0 plus 2 by 1 plus 2 minus 3. And yeah, actually divided by 14. So 1 divided by 14. So this coefficient. And alpha 2 on iteration 3. So we
Це, мабуть, буде мінус 1 ділити на 14. Там 2 мінус 3.
2 мінус 3. Ну,
А у вас не мінус 1 ділити.
у нас мінус
Ну, а ви там
перед
не записали просто.
minus before fraction.
А, все, зрозумів, так.
Yeah,
Не
so
побачив.
everything is okay. Yeah, and 2 became a lambda. Let's correct it. Yeah, but feel free to ask questions, of course, if you hesitate. Okay, and how to find alpha 2, 3? So this is the scalar product of f2 multiplied by g3 and divided by scalar product of f2 by itself. So f2 is equal to g2. It just so such wacky case. So the scalar product is 3 plus 3. 6, and the scalar product over f2, so 9 plus 4, and it will be minus 6 divided by 13. Yeah, but let's verify. So 3 by 2. Sorry. Yeah, it was a mistake. So f2 and g3. Yeah, need to correct it. Minus 5 divided by 13. And our so f3 vector coordinates. Let's copy and paste this formula. So now the board becomes, so we need more and more space on our board. More and more. So f3 equals, so g3 this vector plus, so alpha 1 divided by 14 0 3 minus 2. Oh, no, f1, and f1 is 1 2 3 plus and plus f2 minus 5 divided by 13 by 0 3 minus 2. I like this fractions 14 13. Okay, but nevertheless we need to add them. So 0 plus 1 14, so 1 14 minus, just 1 divided by 14. Okay, and then 2 divided by 14, and 3. Oh no, 2 divided by 14 minus 3 divided by 13. And 3 divided by 14 plus 10 divided by 13. Okay, so let's just entertain. So if I'm not mistaken, so okay, let's just quick calculate 13 by 14. So 182. Uh, so 26 minus 42. $39 plus 140. And finally, or maybe not finally, so 26 minus 42 minus 16 divided by 182. And 179 divided by 182. Well, this so y can be shortened. Let's do it. So minus 8 divided by 91. And this cannot be shortened, so will remain like this. Maybe hurried a little bit. So now what we have to do, we need to verify that this basis is orthonormal. So no, firstly that vectors f1, f2, and f3 are orthogonal. It means that we need to multiply it one by each other. So f1 multiplied by f2. Let's multiply. So 1 by 0 plus 2 by 3 that equals 0. Okay, this is correct. And now let's do the same for f1, f2. Oh, okay, f2, f3. Of course, we need to do it as well for f1, f3, but we don't have enough time. So 0 plus, so 3 by 8, minus 24 divided by 91, and ah, I forgot to add these numbers. Okay, so currently we have not enough time to finish it because we need to also to look at the next task. But what is the idea then how to move to orthonormal basis? So just what we need to do. So we need to normalize all vectors in such way. So just find unit vectors over each of them, for each of them. You will finish it at home. I will try to do the presentation, but it will be at the weekend, yeah, because I know this topic is a little bit hard for understanding. Maybe any questions about this task? Or no questions?
No questions.
No questions.
I see a message in the chat. Coordinator. Yeah, thanks, Valeria, but feel free to raise your hand, of course. Yeah, so I don't always look into the chat, but everyone try to raise your hand and say if you have no problems with the microphone. Yeah, we just made a mistake. I made a mistake, and F3 is incorrect. And now we have to solve one more task, task 8. So now, what do you remember about unitary spaces, Hermitian product? Don't remember, right? Okay, I will remind you. So it is a space of complex vectors. So you already had lectures about complex number, as I know, and we also have complex vectors, so they can have imaginary parts. And as we see, vector A and vector B have imaginary parts. How to find how works the scalar product of vectors in so in Hermite space. Yeah, so Hermitian product is a scalar product in the unitary space, and we just do like that. So x a multiplied by xb, and it is complex. Complex, forgot this definition. Комплексно спряжене. So that means that the imaginary part is has the other sign. So why looks like that, and the magnitude is quite similar to the linear space. So Euclid space, actually the same definition, but we need also to remember about so the rule about scalar product, Hermitian product. So let's find vector magnitude of vector A and how to do it. So we multiply two, so 2 by 2, because these parts are, so we have only real part for x, and for y coordinate, so 2 minus I multiplied by 2 plus I, and square of I, as you remember, equals -1. So 4 plus 2 plus 1. Yeah, I forgot about square root and nobody told me. Where's your attention? And it equals 7. So here is it. Okay. Now we need to multiply A by B. how to do it. So 2 multiplied by 3 minus I, because we change the sign of imaginary part, plus of B vector, plus 2 minus I multiplied by 2. And it equals 6 minus 2I plus 4 minus 2I. And the final answer, 10 minus 4I. Any questions to this task?
No question.
About the lesson in general, maybe about previous lessons? Sophia?
I have a question about this exercise. I just maybe I don't remember why we changed the sign of the imaginary part.
So complex. Okay, let's translate it, by the way. So комплексно спряженное число. English complex. So complex conjugate number. So do you remember complex conjugate number, what it means? So we have a number z, complex number x plus y multiplied by I, and the complex conjugate number, it is the number that has the imaginary part of opposite sign. So do you remember it from the lectures? So any questions about it?
No questions, thank you.
Okay, no questions. So have a nice day, stay safe. Thanks for your attention. Goodbye.
Goodbye.
Bye.
Thank you for listening. Bye.
Thank you for the lesson. Goodbye.
Bye.